Hello my friends and welcome to the You Can Do TV channel. In this video we will explore powerful shear, crusher and shredder for scrap car recycling. This powerful machine is Genesis XT Mobile Shear, manufactured by Genesis Attachments, LLC, based in Wisconsin, USA. Bolt-on piercing tip encapsulates front of upper jaw, minimizing risk of damage while reducing welding buildup and downtime. Short primary cutting blades position the apex closer to the rear of the jaws and draw material further into the jaws where high force makes efficient cuts. Lower shear height improves visibility. It is designed to process steel and other materials more efficiently in scrap and demolition applications and fit on smaller carriers, reducing initial acquisition investments and hourly energy consumption costs. This scrap and demolition shear features improved jaw geometry that makes it easier to pick up material and reduces ground contact wear. A reverse-mounted hydraulic cylinder that shortens shear length and reduces weight. A weld-on, replaceable, highly abrasion-resistant steel rhino horn that protects the front of the upper jaw, reducing welding buildup. This is Cayman Demolition Shear manufactured by ZATO SRL, Italy. It is a highly efficient hydraulic demolition shears for recycling medium and heavy ferrous and non-ferrous materials. Cayman effectively reduced the size of steel and aluminium bars, profiles, downsize bulky scrap and facilitate the recovery of recyclable materials and residues. Manufactured in Italy, Cayman Demolition Shears integrate state-of-the-art technology with innovative cutting geometries. The exceptional cutting force of Cayman demolition attachments are due to the combined effect of high-performance cutting blades, reliable gearboxes and a robust machine body. The wide jaw opening of the Cayman demolition shears guarantees high cutting performance while a large discharge area ensures smooth clearance. The center pivot is designed to resist thrust damage thanks to a specific manufacturing procedure known as cryogenic capability. The pivot is cooled using liquid nitrogen before fitting into the housing. The gradual return to ambient temperature favors the perfect fit of the pin in its housing, thus ensuring better durability and reliability. Unmistakable in its distinctive line, the middle one along the sides and the one on the movable beak. Extraordinary cutting capacity thanks to blades reversible up to 4 times. Second guide of the jaw and the tip covered by the blade. Improved operation, maintenance performance of the shear. The powerful cylinder, along with the aggressive geometry of the cutting area, allows excellent performance. reinforced high-strength steel body with wear-resistant steel parts, Strenex and Hardox. Exclusive technologies of cutting blades, gearboxes, and regenerative valves. The shears are suitable to be employed in all harsh working conditions. The Bronneberg Car Baler is an easily transportable car baler and can be fitted with a container hook system or hydraulic lifting jacks. The Bronneberg Car Baler produces high-density bales from ferrous and non-ferrous scrap metal, as well as ELV and car scrap. This baler machine is mounted onto a self-supporting frame with an integrated hydraulic power pack and a 145 HP diesel engine. Due to possessing the widest box opening of its category, the Bronneberg Car Baler can easily be loaded with a grapple. It has been designed to hold large-size vehicles and to accelerate the box closing system in order to increase the hourly production. The 200 tons pre-compression force of the lid makes sure that even large-sized vehicles will be compacted in the box before the actual baling process can be started in an automatic cycle. The final pushing baling force is, with 160 tons, the highest in its class. The Bronneberg Car Baler features a unique charging box which enables the operator to squeeze material in quickly, without losing valuable time. When the charging box is closed, the car baler is able to produce a high-density bale in less than 60 seconds. The car baler press is manufactured to compact and shear most grades of scrap metal. The Bronneberg baler machine is ideal for companies dealing with mixed scrap and cars on an ongoing basis. Here you can see a stationary variant of Arger's high-performance shredder VZ950 shredding car bodies. The machine is driven by two powerful electric motors, each with an output of 250 kilowatts. After the removal of saleable used parts, end-of-life vehicles are shredded and the materials are separated into different fractions, such as metals, light metals, plastics, etc. The share of scrap will be processed for the further usage and production of new steel. Lengthwise, built-in rigid permanent magnet for effective phase separation. The slow-speed two-shaft principle is the basis for all primary shredding solutions. Depending on material, the configuration of shaft geometry, hooks, paddles, plates, blades, requires adjustments to achieve the best shredding results. Powerful Volvo Penta diesel engine for the maximum efficiency during the shredding process. Discharge belt for lateral discharge of the separated non-ferrous fraction. This is OKADA Cross Cutter. It is manufactured by OKADA, Japan, with operating weight 2,540 kilograms. The special casting alloy used delivers a lightweight crusher with superior durability. the arched cutter blade provides robust cutting ability. Adopts the press and cut method. A high oil flow speed valve reduces cycle time. The robust rotator features a durable bearing. End-of-life vehicles, ELVs, represent a significant source of recyclable materials. The process of pulling apart and recycling these vehicles involves several stages, each meticulously designed to maximize the recovery of valuable components and minimize environmental impact. This intricate procedure is essential for sustainable automotive industry practices and for reducing the accumulation of waste in landfills. Initial assessment and depollution. The first step in the recycling process is the initial assessment of the vehicle. At this stage, the vehicle is inspected to identify any hazardous materials that need special handling. This includes fluids such as oil, fuel, coolant, brake fluid, and refrigerants. The depollution process involves draining these fluids to prevent environmental contamination. Additionally, components like batteries, airbags, and mercury switches are removed to ensure they are disposed of or recycled properly. Dismantling and part recovery. Once depollution is complete, the vehicle undergoes dismantling. This involves removing reusable and recyclable parts. High-demand components such as engines, transmissions, and catalytic converters are carefully extracted. These parts are often refurbished and resold, contributing to a circular economy. The dismantling process is significantly aided by specialized equipment like mobile material handling machines. These machines are designed to efficiently and safely disassemble vehicles. Their high-performance capabilities allow for the rapid lifting and moving of heavy components, ensuring that even the most robust parts can be extracted without damage. The versatility of these machines, with attachments tailored to specific tasks, ensures optimal performance in various dismantling applications. Shredding and material separation. After valuable parts are removed, the remaining vehicle shell is sent to a shredding facility. Here, the vehicle is broken down into smaller pieces using powerful shredders. This creates a mix of materials, including metals, plastics, and glass. The next step involves separating these materials for further processing. Advanced separation techniques are employed to sort the shredded material. Magnetic separators extract ferrous metals like steel, while eddy current separators are used for non-ferrous metals such as aluminum. Other technologies, such as flotation and air classification, help separate lighter materials like plastics and foam from heavier ones. The goal is to create clean streams of specific materials that can be sent for recycling. Recycling of metals. The separated metals are then sent to recycling facilities where they are melted down and purified. Steel and aluminum, being the primary metals in vehicles, are recycled extensively. The recycled metal can be used to manufacture new automotive parts or other products, significantly reducing the demand for virgin materials. This not only conserves natural resources but also requires less energy compared to producing metals from raw ore, thereby reducing greenhouse gas emissions. Recycling of non-metallic components. Non-metallic components such as plastics, rubber, and glass also undergo recycling. Plastics are sorted by type and either melted down to create new plastic products or chemically processed to break them down into their original monomers for reuse. Rubber, especially from tires, is often ground into crumb rubber and used in various applications like asphalt or playground surfaces. Glass from windows and lights is crushed and purified, ready to be melted and formed into new glass products. The role of mobile material handling machines. Mobile material handling machines play a vital role throughout the dismantling and recycling process. These machines are designed for high performance, ensuring stability and power in lifting and loading operations. They can be equipped with a variety of attachments, such as grapples and shears, allowing them to be optimally matched to specific tasks. This versatility makes them indispensable in efficiently dismantling vehicles and handling heavy components safely. Their design ensures that they can operate in various environments, whether in a dismantling yard or a recycling facility. The overall stability and maneuverability of these machines mean that they can handle large volumes of vehicles and materials quickly, thereby speeding up the recycling process and improving overall productivity. Environmental and economic benefits. Recycling vehicles at the end of their life cycle provides substantial environmental and economic benefits. By recovering and reusing materials, we reduce the need for mining and manufacturing new raw materials, which in turn lowers energy consumption and greenhouse gas emissions. The sale of reusable parts and recycled materials also provides economic incentives, creating jobs and supporting industries involved in the recycling chain. Steel is 100% recyclable, making it one of the most environmentally friendly materials available. Despite its ubiquitous presence in our daily lives, steel often goes unnoticed. This versatile material can be manufactured through various technologies, and this discussion will focus on the production and processing of steel at Żelazniarne Podbrzeżowe, one of Europe's leading steel companies. The journey of steel production begins with the preparation of the primary input material, steel scrap. The process starts at authorized recycling centers where liquids are drained from the cars, and plastic, glass, and non-ferrous materials are separated and disposed of. The cars are then crushed and shredded, with non-ferrous metals and other impurities being removed in the process. The result is a reduced volume of clean scrap, which becomes the basic feedstock for melting in the electric arc furnace. Steel production at Podbrzeżowe has a long and illustrious history, marked by several milestones. For instance, the first steel was produced at this site in 1851, and the first Siemens Martin furnace in Slovakia was operational by 1879. Furthermore, the first continuous casting facility in Czechoslovakia was introduced here in 1961. At the heart of the mill is an electric arc furnace capable of melting up to 60 tons of scrap per hour at a temperature reaching 1620 degrees Celsius. The liquid steel is then transferred to a ladle, where primary alloying takes place during the tapping process. Additional alloying elements are added in the ladle furnace to achieve the desired steel quality. The molten steel is continuously cast into blooms with square or circular cross-sections. After cutting, marking, and cooling, the final quality control is performed before the blooms are transferred to the rolling mill. With an annual production capacity of 370,000 tons, if the steel blooms were placed end to end, they could form a continuous line stretching from Podbrezova to Brussels. The Podbrezova facility was the first tube rolling mill in the Austro-Hungarian Empire, with the first tube being manufactured in 1883. Over the years, technology and production methods have been modernized and made more efficient. In the tube rolling mill, steel blooms undergo significant transformation. For example, a bloom with a 200 mm cross-section is reduced to a tube with an area 160 times smaller. The steel blocks are cut to the desired length using hydraulic shears or sawing with a slitting saw. These blocks, approximately 1 meter long, are then heated to the rolling temperature in a rotary furnace. They are subsequently formed into circular molds on the piercing press. The molds then pass through an elongation and processing mill, where their length is increased by approximately 20 times from their original form. After milling and the removal of the mandrel rods, the semi-produced product is rolled in the drawing reduction mill to achieve the desired dimensions, with the length of each tube reaching up to 90 meters. Annually, more than 1 million tubes are manufactured using this method. After cooling, the rolled tubes are cut to the requested length, followed by quality control, smoothing of the burrs at the ends, and final operations such as labeling and packaging as specified by the customer. The daily production amounts to about 25 truckloads of tubes. Part of the production is shipped directly to customers, while another part is transported for further processing to the tube drawing mill. In the tube drawing mill, the rolled tubes are hot swagged by drop forging to form a gripping part. They are then placed into hydrochloric acid, which removes surface dirt and scale. A primary phosphate and soap layer is applied to reduce material resistance during cold forming on linear drawing benches using a die plate or mandrel, ultimately achieving the desired dimensions, including diameters as small as 3 millimeters. One of the critical processes in steel production is the drawing of tubes, which can involve reducing the diameter from 32 millimeters through 9 stages. During this process, a device generates a pulling force equivalent to 10 railway locomotives, causing deformation and changes in the crystalline structure of the steel. This process makes the tubes less rigid and more fragile, necessitating annealing in a continuous furnace under a protective atmosphere to restore the required mechanical properties. Following heat treatment, the tubes either undergo further processing or move to finalization. The finalization process includes several manufacturing steps. Straightening ensures the tube's required flatness. Non-destructive testing discards any tubes with defects. Cutting provides the desired length. And visual inspection verifies the dimensions and exterior quality of the tubes. Finally, the tubes are packed into bundles and shipped to the customer. Galvanized tubes, designed for hydraulic and pneumatic pressure distribution, make up a significant portion of manufactured precision tubes. The galvanization process enhances the tube's properties, providing a premium product with a zinc coating that serves as an electrochemical barrier against corrosion and improves aesthetic appeal. This coating is applied electrolytically in a continuous double twin line, followed by a layer of chromium over the zinc-covered surface for added protection and finish. Production of precision-drawn tubes and shaped profiles of carbon or low-alloy steel also occurs in Zileziyarne Podbrezheva's subsidiary companies. The starting stock here is an entry rod produced at Zileziyarne Podbrezheva, with production utilizing continuous drawing on linear and drum benches. This technology allows precision steel tubes with diameters up to 60 millimeters to be supplied in coils, which can reach lengths up to 560 meters. A computerized finishing warehouse provides additional insulation using polyolefin surface protection, complementing the production of electrolytically galvanized tubes. Tube fittings, made from rolled tubes through hot forming, complete the product range. These include elbows and reducers, which are especially crucial for the automotive industry. Here, tubes are sawn, deburred, and bent according to customer specifications using modern technological equipment. At first glance, steel tubes might seem simple, but their production involves numerous intricate processes. Each tube undergoes multiple operations, including heating, cooling, and cutting, to meet its specific purpose. These tubes are essential before they transport gas or oil, deliver water, become part of vehicles, conduct heat, or serve various designs. Seamless cold-drawn stainless steel tubes with a large diameter represent a pinnacle in advanced manufacturing, combining high precision, excellent surface finish, and superior mechanical properties. These tubes are critical in various high-stress applications, including in the oil and gas industry, chemical processing, and power generation. The production process for these tubes leverages a hydraulic cold drying machine with a remarkable overpower capacity of 650 tons, enabling the manufacture of large diameter tubes with exceptional precision and quality. The process of cold drying involves pulling a stainless steel billet through a die to reduce its diameter and increase its length. This process is typically done at room temperature, which helps in maintaining the mechanical properties of the stainless steel while also improving its surface finish and dimensional accuracy. For large diameter seamless tubes, the hydraulic cold drying machine's capacity is crucial. A machine with over 650 tons of power capacity can exert substantial force, essential for shaping and refining large, thick-walled tubes. Seamless tubes, unlike welded tubes, do not have a welded seam, making them stronger and more reliable under pressure. The absence of a seam ensures uniformity in the tube structure, which is particularly beneficial in applications requiring high durability and resistance to various stresses in corrosive environments. Stainless steel adds another layer of advantage, providing excellent corrosion resistance, high strength, and low maintenance requirements. The use of a hydraulic cold drying machine with over 650 tons of capacity brings several benefits to the production of large diameter seamless tubes. First, it allows for the creation of tubes with precise dimensions and tight tolerances, crucial for applications where exact specifications are necessary for performance and safety. Second, the high power capacity of the machine ensures that the cold drawing process can handle larger and thicker billets, expanding the range of possible tube sizes and applications. Moreover, the hydraulic system in such a machine provides smooth and consistent force, reducing the risk of defects and ensuring a high-quality finish. This consistency is vital for maintaining the integrity of the stainless steel's mechanical properties, such as tensile strength and hardness, which are critical in demanding applications. The China Top CNC 3/4 rollers plate rolling machine, designed for bending plates, offers exceptional performance and versatility. It seamlessly executes pre-bending and bending operations without the need for reversing the plate. With supplementary devices, it can shape plates into tubular, arc, or cone-shaped workpieces, catering to various industries including warfare, energy, transportation, and more. Key components include fixed top and bottom rollers, with computer-controlled vertical and horizontal movement of the bottom and side rollers. This precise control ensures a synchronous accuracy of plus or minus 0.2 mm, displayed on an LCD screen. The machine's four-roller design offers several advantages: pre-bending and bending without reversing, alignment via side rollers, rough leveling of plates, regulation of defective cylinders, and ease in bending cone-shaped workpieces. The machine comprises framework, roller, tilting, transmission, hydraulic, electrical, lubrication, and foundation sections. Heavy-duty, low-loss center adjusting rolling bearings support the rollers, crafted from high-quality No. 45 carbon steel. In this section, we will visit Türkiye's leading wheel factory, Jansa. Here, we will explore the production process of wheels for tractors, agricultural, mining, industrial, military, heavy-duty. The factory's wheel manufacturing process begins with stringent raw material preparation. Sourced from reputable suppliers, materials undergo rigorous testing in-house. Shot blasting cleans, strengthens, and polishes metal, with a focus on high-strength steels for lightweight yet robust construction. Utilizing two automatic steel decoiling lines, the factory crafts discs ranging from 4 mm to 19 mm thick and rims from 3 mm to 12 mm thick. Advanced laser cutting capabilities cater to specialized design requests. Rim profiling, conducted across 9 manufacturing lines, offers an industry-leading range of diameters and widths. Automation minimizes errors, ensuring peak production efficiency. Flow-forming technology reduces wheel weight without sacrificing durability, while unique traceability markings enable life cycle tracking. High spot marking optimizes tire mounting, especially for agricultural flotation wheels. The increasing speed, weight, payload, and horsepower of contemporary vehicles demand precise wheel dimensions to ensure optimal safety and driving comfort. At each critical stage of production, the wheels undergo thorough inspection, including 100% control for radial and lateral runout. Discs are manufactured through stamping and CNC machining on 8 production lines, with mass-scale production benefiting from advanced robotics automation. Each disc undergoes unique traceability stamping, akin to rim production. Welding for disc and rim assembly varies based on product type and material quality, utilizing either automated welding robots or manual processes with inert gas and submerged arc welding. Stringent quality control measures ensure precise lateral and radial runout for all wheels. Surface treatment is paramount for longevity and corrosion resistance. Shot blasting maximizes rust resistance, followed by automotive standard double anti-corrosion protection through zinc phosphate pre-treatment and epoxy E-coat. Cathodic dipping safeguards hard-to-reach areas, with lead-free paint minimizing environmental impact. These wheels boast salt spray rust resistance of up to 1,000 hours and offer over 200 paint options, meeting stringent requirements across heavy equipment categories. Producing an electric kettle involves a series of intricate steps in electrical process technology. Today, we're going to take you on a journey through Taipeng factory to understand how electric kettles are made, right from the acquisition of hardware parts to the final product packaging. Material procurement and preparations. Our journey commences with the acquisition of premium-grade stainless steel, meticulously selected to ensure durability and longevity. Cutting-edge machinery transforms these raw materials into the foundational components of our electric kettles, slicing through steel sheets with precision akin to scattered grains. Shaping and structural integrity. Behold our stretch machine, a marvel of engineering prowess. It molds the steel sheets, shaping them into the robust framework of the kettle body. Careful attention is paid to the thickness of the steel, an essential factor to prevent deformations that might compromise the kettle's integrity. Assembly and functional testing. Witness as skilled hands assemble the disparate parts, uniting them into a cohesive whole. The kettle switch undergoes scrutiny under steam, ensuring operational excellence. While the initial form may lack luster, a touch of mechanical finesse and meticulous assembly elevates its appeal, transforming it into a polished masterpiece. Precision in detailing. Enter the domain of precision detailing, where machines craft the delicate spouts and handles that adorn our kettles. Each component is meticulously attached, ensuring a seamless blend of form and function. Ultrasonic cleaning and refinement. As the kettle nears completion, it undergoes a thorough ultrasonic cleansing, purging any vestiges of impurity that may mar its surface. From aluminum housings to heating elements, every part is meticulously welded, guaranteeing a seamless union that withstands the rigors of daily use. Welding and assembly. After cutting and shaping, the individual components are assembled using welding techniques. Welding machines are employed to fuse the steel components together, creating a seamless and durable kettle body. Steam is utilized to test the functionality of the kettle switch, ensuring proper operation before proceeding to the next step. Polishing and finishing touches. The assembled kettle body undergoes a polishing process to enhance its appearance and remove any surface imperfections. Polishing machines equipped with abrasive materials work to achieve a smooth and lustrous finish on the stainless steel surfaces. This step is crucial for improving the aesthetics of the electric kettle and enhancing its overall appeal to consumers. Handle and spout attachment. Handles and spouts are carefully attached to the kettle body using specialized machinery. Automated assembly machines ensure precise alignment and secure attachment of the handle and spout, contributing to the functionality and ergonomic design of the kettle. Ultrasonic cleaning. To remove any residual dirt or contaminants accumulated during the manufacturing process, the kettle undergoes ultrasonic cleaning. Ultrasonic cleaning equipment utilizes high-frequency sound waves to dislodge and remove particles from the surface of the kettle, ensuring it meets stringent cleanliness standards. The heating elements, critical components of the electric kettle, are produced using high-frequency induction heating technology. Skilled workers assemble the heating elements, which consist of heating coils encased protective casings, ensuring they meet quality specifications. Plastic housing injection. Plastic components, including the handle, lid, and base of the kettle, are manufactured using injection molding machines. Molded plastic parts are produced with precision and consistency, ensuring uniformity in size and shape. Heating wire installation. Heating wires, responsible for heating the water in the kettle, are carefully installed onto the heating elements. Skilled technicians ensure proper placement and connection of the heating wires to optimize heating efficiency and performance. Quality assurance and testing. Our commitment to excellence extends to rigorous quality control measures. Each heating plate undergoes meticulous testing, with only the finest specimens earning the seal of approval. Plastic housing injection and integration. Enter the realm of plastic housing injection, where molten polymers take shape, giving rise to the ergonomic handles and lids that grace our kettles. With precision and care, heating wires are integrated into the heating elements, ensuring seamless functionality and optimal heating efficiency. Base assembly and testing. The base assembly involves integrating the heating elements with the electrical components and power cord. Comprehensive testing, including high-voltage tests, is conducted to verify the functionality and safety of the kettle before final assembly. Final quality checks. Before packaging, the finished electric kettle undergoes rigorous quality control checks. Quality inspectors examine the kettle for defects, ensuring it meets all quality standards and specifications. Packaging and shipping. Once the kettle passes all quality checks, it is carefully packaged to protect it from damage during transportation. Packaging materials are chosen to ensure the safety and integrity of the product during shipping. The BOLDRINI portal frame press model POW 1000X9100 operates through a series of precisely orchestrated steps to produce high-quality dished heads for tanks and pressure vessels. Loading and preparation. Initially, cold blanks are loaded onto the press bed. These blanks are typically large metal sheets with predetermined dimensions and thicknesses. Manipulation and handling. The CNC manipulator, a sophisticated handling device, takes control. It moves the blanks into position, ensuring they are properly aligned and secured for the pressing process. Pressing. The press exerts immense force, up to 1,000 tons, onto the blank. This force causes the metal to deform, taking on the desired shape of a dished head. The CNC manipulator ensures precise movement and pressure distribution throughout this process, contributing to the uniformity and quality of the final product. Forming. As the press applies force, the metal gradually forms into a smooth, curved shape with a regular spherical profile. This process requires precision and control to achieve the desired dimensions and surface finish. Unloading. Once the pressing is complete, the CNC manipulator carefully removes the formed dished head from the press bed. The finished heads are then ready for further processing or assembly into tanks and pressure vessels. Coil winding. Transformer windings are designed to meet three fundamental requirements, viz. Mechanical, thermal and electrical. They are cylindrical in shape and are assembled concentrically. Paper-insulated conductors of high conductivity and soft-drawn electrolytic-grade copper is used which comply with international standards. Windings are made with great care by well-experienced skilled disc winding workers in dust-free and temperature-controlled environment. The most significant material in a transformer is the core. High-quality cold-rolled grain-oriented magnetic silicon steel should be used to ensure optimum losses and most efficient working of the transformer. The type of magnetic steel is chosen according to the desired loss level. The laminations are cut geometrically to ensure optimum flow of magnetic flux and minimum air gap between the joint of two consecutive sheets. The core is designed with safe flux density to minimize core loss and magnetizing current. The laminations are handled with utmost care to preserve magnetic properties. Coil design and quality are keys to transformer efficiency and longevity. Thermally upgraded paper should be used for longest insulation life. Coils are assembled with best insulating materials and are adequately clamped. The ends and tapping leads of all windings are connected by special extra flexible, insulated copper cables which are rigidly braced in position. Complete assembly of the remaining parts of the transformer. Finally, the transformer is transported to the construction site. Here it is installed and tested before being put into use. The actual chip production takes place in a fabrication area, commonly referred to as a fab. Micron's fabs are state-of-the-art clean rooms, boasting an environment that's 100 times cleaner than a hospital operating room. This ensures that the pure silicon wafers, which individual memory chips or die are built upon, remain uncontaminated. Photolithography, a key step in the fab, involves coating wafers with a photoresistant material. Circuit patterns are then exposed, resulting in ultra-fine pathways on the wafer. Advanced robotics shepherd these wafers through a myriad of processes, a journey that spans weeks. Before assembly, the crucial probe step comes into play. Each die on the wafer undergoes an initial functionality test using a probe card equipped with tiny needles. This card interfaces with each die, transmitting and receiving test data. This step is vital as it identifies and filters out any defective dies, ensuring only the best proceed to the assembly phase. In assembly phase, wafers are first thinned and adhered to an adhesive backing for stability. Using a precise diamond-edged saw, the wafer is diced into individual dies. Guided by the wafer map from the probe step, qualified dies are selected and placed onto circuit boards. Solid gold wires connect each chip to the board, ensuring optimal conductivity. Each die is then encapsulated in a protective plastic mold, safeguarding it from environmental factors before proceeding to further testing. Every memory chip is subjected to rigorous testing to uphold unparalleled quality standards. Utilizing specialized equipment, these chips face extreme conditions, ensuring only the robust components make their way to consumers. Beyond just functionality, Micron ensures each chip not only meets but often surpasses its designated performance benchmarks. Once these stringent tests are passed, chips are distinctly laser engraved with identification markers, ensuring traceability and authenticity. A meticulous optical scan further ensures that each chip adheres to exacting fit and form criteria. Safety and quality don't end at the chip level. These chips are securely housed in industry-standard anti-static packaging, safeguarding them from potential hazards. Many of these high-quality chips find their purpose in memory modules and solid-state drives. Leveraging state-of-the-art assembly machinery, chips are seamlessly integrated onto circuit boards. Before these products reach customers, they undergo one final round of exhaustive testing. Here is Yorkville Sound's manufacturing facility located in Pickering, Ontario, Canada, a suburb of Toronto. Founded in 1963, Yorkville Sound is the manufacturer of Yorkville-branded PA loudspeakers and electronics, Trainer instrument amplifiers, VTC Pro audio touring systems, accessories and hardware. Upon entering the woodshop, one is immediately greeted by the sight of large slabs of timber, each waiting to be transformed. These machines are the silent artists, carving wood components used in solid plywood cabinet construction with meticulous precision. The commitment to resource optimization is evident, with CNC programs designed to maximize the use of every raw sheet. Venturing further, the cabinet assembly area is a symphony of coordination and precision. Here, pieces sculpted in the woodshop are assembled into speaker cabinets. Precision jigs, high-tensile glue, and brad nails work in unison to ensure perfect alignment and stability. The workflow is a well-choreographed dance, with two parallel lines operating to maximize efficiency through this production phase. While 15mm Baltic birch plywood is a staple for its ruggedness and reliability, select products feature poplar or fir della, catering to preferences for a lighter, more resonant cabinet design. The meticulous attention to detail is palpable, with every imperfection addressed and every surface sanded and sealed before painting. The journey of each cabinet continues through automated overhead conveyors to one of the 4 in-house paint booths. Whether it's a rugged ultra-thin painted finish or a black rubberized epoxy coating, each cabinet is hand-painted by highly skilled technicians, allowing for careful attention to detail and a final inspection before final production. The commitment to environmental sensitivity is commendable, with the use of eco-friendly materials and advanced paint booths designed to recover all overspray. Finally, the painted cabinets move to their final destination, the finishing line, where they are completed with the installation of speaker components and other finishing touches. One of the standout features is Yorkville's in-house manufacturing of all essential metal components for their products. A visit to their metal shop offers a captivating view of where amplifier chassis, speaker grills, powered speaker amp bodies, and other crucial materials come to life. The shop boasts state-of-the-art machinery, including several computer-controlled presses and punches. It's fascinating to watch a chassis for one of their latest bass heads evolve. What starts as a flat metal sheet, meticulously cut and punched by their advanced machinery, is then skillfully hand-bent into its final form. Another intriguing process is the shaping of their custom perforated speaker grill material. The sight of completed, elegantly curved grills, ready for installation, is a testament to their attention to detail. To enhance durability and prevent rust, these metal components undergo a powder coating process. This method, distinct from the traditional wood cabinet painting, is executed in a dedicated, eco-friendly section of their facility. The variety of powder coat colors, textures, and finishes cater to the diverse product lines and brands birthed in their Pickering factory. Beyond the larger components, the metal shop's efficiency shines in the rapid fabrication of smaller precision parts, such as badges and control panels. They even manage their chassis screening and color inkjet printing in-house, further optimizing their production speed. Continuing the exploration, the next stop is the sector of the factory dedicated to crafting the vital electronic components of the products. Witnessing the newly acquired SMT machine meticulously installing small surface mount parts on one of the high-tech digital amplifiers is a spectacle of precision and technology. The design process here is robust, incorporating proven, rugged, and reliable through-hole parts, large ICs, film capacitors, and ceramic resistors, all requiring specialized auto-insertion technology. Observing the larger through-hole parts and ICs being integrated into a circuit board by one of the auto-insertion machines in the printed circuit board assembly area is a testament to Yorkville's commitment to quality and precision. The more intricate components are manually added by highly skilled technicians in the electronics assembly area, where elements like LEDs, switches, inductors, and capacitors are meticulously added to the boards, and any necessary point-to-point wiring is executed with precision. The sight of larger components like tube sockets and connectors being installed and hand-soldered is a vivid display of craftsmanship and technical acumen. Witnessing the finished circuit boards, ready for the final wave solder process, is a clear indication of the meticulous journey each component undergoes. This RoHS-compliant process seals the boards and solidifies all the electrical connections in mere seconds, leaving them ready for testing and inspection before being integrated into the chassis and cabinets previously observed in the metal shop. The convergence of the completed printed circuit boards and the meticulously fabricated metal chassis in the wiring line is where the product truly begins to manifest its final form. Here, printed circuit boards from the electronics assembly merge seamlessly with metal facades crafted in the metal workshop. A range of sophisticated products, from amplifiers and mixers to specialized electronic subassemblies tailored for powered speakers, and even guitar and bass combo amplifiers. The dedication to perfection is evident, with meticulous attention at every assembly juncture. Notably, several finished amplifier subassemblies stand ready for integration into powered speaker cabinets. Each unit undergoes rigorous testing, ensuring every component aligns with design expectations. Any anomalies prompt immediate rectifications, be it minor tweaks or circuit board adjustments. Post-assembly, products undergo a 24-hour burn-in, reinforcing their reliability. The heart of the factory lies in its finishing and final assembly area. This expansive section, spanning a massive 150,000 square feet in Pickering, is a hive of activity. Three distinct assembly lines work in tandem, meticulously crafting PA speakers, subwoofers, and even guitar and bass cabinets. The attention to detail is palpable, from the hand-affixed coverings on the Elite and YX loudspeaker products to the intricate assembly of Powerline Series ABS cabinets. Each station along the lines has a specific role, from installing internal bracing and crossovers to attaching handles and grills. Quality is paramount. Every product undergoes rigorous visual inspections and, ultimately, a comprehensive QC check. Here, a dedicated technician subjects each piece to an audio precision test, ensuring it performs to design specifications. Only after passing this stringent process does a product receive its serial number, ready for packaging and shipping. Ensuring the product reaches customers in pristine condition, regardless of their global location, is a priority. The final journey begins in a climate-controlled warehouse, ready for dispatch. Behind these products is Yorkville's adept engineering team, based in Pickering. Their state-of-the-art labs, equipped with the latest CAD and bench test equipment, are where innovations come to life, from tube amplifiers to LED lighting. This end-to-end in-house approach is truly commendable. In this part, we'll delve into the key stages of speaker production at Shear in Italy. The process begins with the magnet assembly. This component plays a crucial role in the speaker's function, creating the magnetic field necessary for sound generation. High-quality magnets are carefully selected and aligned to ensure optimum performance. The speaker cone is the part that physically moves to produce sound. It is typically made from materials like paper, polypropylene, or other composites. The cone's size, shape, and material are engineered to produce specific frequency responses and sound characteristics. The surround is the flexible ring that attaches the cone to the speaker's frame. It allows the cone to move while maintaining a proper seal. Surrounds are molded to precise specifications to ensure optimal performance and durability. Proper adhesion between the cone and surround is critical. This step involves the careful application of adhesive to create a strong bond that can withstand the forces generated during speaker operation. Free suspension control involves testing the speaker's suspension system, which includes the cone, surround, and spider, a component that helps center the voice coil. Lead wires are attached to the speaker's voice coil, which is responsible for converting electrical signals into sound. These wires must be installed precisely to ensure a secure electrical connection. Waterproof coating. To protect the speaker from moisture and environmental factors, a waterproof coating is applied. This coating helps prolong the speaker's lifespan and maintain its performance, especially in outdoor or high humidity environments. Titanium molding. In some cases, titanium is used for components like diaphragms or tweeter domes. Titanium is known for its lightweight and high-strength properties, which can improve the speaker's overall performance, particularly in high-frequency applications. HF, high-frequency, production. High-frequency components, such as tweeters or compression drivers, are designed and produced separately. These components are engineered to reproduce treble and high-frequency sounds accurately. LF, low-frequency, production. Low-frequency components, often referred to as woofers, are designed to handle the lower range of frequencies. These are larger and more robust components designed to move larger volumes of air. - 100% quality control. Quality control is integrated into every stage of the manufacturing process. Before a speaker leaves the production line, it undergoes rigorous testing and inspection to ensure that it meets the manufacturer's exacting standards for sound quality and durability. The CNC deep drawing lathe, manufactured by Riglamac Machines, represents a significant advancement in automated manufacturing processes, particularly in the production of aluminum frying pans. This innovative machine operates autonomously, utilizing cutting-edge technology to streamline the production process while ensuring precision and efficiency. At the heart of the machine is its CNC, Computer Numerical Control, system, which governs the entire manufacturing process. The operator inputs the necessary parameters and specifications into the control interface, guiding the machine through each step of production. The deep drawing process begins with the preparation of the aluminum sheet, which is loaded into the machine's feeding system. The CNC system precisely positions the sheet within the work area, ready for processing. As the manufacturing cycle commences, the deep drawing lathe's rotating tip engages with the aluminum sheet, applying controlled force and pressure to shape it into the desired form. This rotational movement is meticulously orchestrated by the CNC system, ensuring uniformity and accuracy in the final product. Simultaneously, the machine's tool magazine comes into play, providing a selection of up to 8 specialized tools required for various stages of the production process. These tools are automatically accessed and utilized as needed, further optimizing efficiency and minimizing downtime. One notable feature of the machine is its adaptability to different production scenarios. While the original model operates with manual adjustment of wedges and pistons on the rotating tip, it offers the option to integrate pneumatic pistons for enhanced automation. This flexibility allows for customization based on specific production requirements and operator preferences. Moreover, the machine's capacity for tool doubling significantly enhances its productivity. By incorporating up to 16 tools and initiating production on both sides, the manufacturing time for each part is substantially reduced, offering considerable time savings for various industries. The versatility of the CNC deep drawing lathe extends beyond aluminum frying pans, with the capability to produce an array of components and products. From molds and baking trays for confectionery to industrial utility parts and decorative lighting items, the machine caters to diverse manufacturing needs with precision and reliability. Additionally, the machine's compatibility with different voltage specifications, including 110V or 220V single-phase and 220/380V three-phase, ensures seamless integration into various operational environments, further enhancing its accessibility and utility. In the heart of Augsburg, Germany, lies the Fujitsu Digital Smart Factory, one of the world's most advanced IT production facilities. Let's delve into the intricate processes. The factory boasts an impressive daily capacity of producing 9,000 units of mainboards. Each of these mainboards begins its journey with a unique identification. The printed circuit board, PCB, is labeled with a distinct serial number. Surface Mount Technology, SMT, for the PCB. The SMT process for the lower side of the PCB involves 3 crucial steps. Screen printing. This is the initial phase where solder paste is applied to the board. It ensures that the components will adhere correctly during the soldering process. Pick and place components. Precision is key. Automated machines meticulously pick and place the required components onto the PCB. Reflow soldering. The PCB is then passed through a reflow oven, where the solder paste melts and solidifies, ensuring the components are firmly attached to the board. For the upper side of the PCB, the process is slightly abbreviated but equally rigorous. Screen printing. Similar to the lower side, solder paste is applied to ensure component adherence. Pick and place components. Once again, machines with pinpoint accuracy place the components onto the PCB. Human-robot collaboration, the future of manufacturing. A significant highlight of the Fujitsu facility in Augsburg is the groundbreaking collaboration between humans and robots. In partnership with automation leader KUKA, Fujitsu has integrated robots that work hand-in-hand with human colleagues. These robots are equipped with sensors that detect the proximity of humans, adjusting their speed to ensure safety. The robots are trained by humans through manual guidance, with machine learning embedding each step into the robot's operations. Through hole technology, THT, process. THT is another essential process in mainboard production. It involves automated insertion of THT components. Machines are employed to insert components that require through-hole mounting. Manual insertion of THT components. Some components, due to their complexity or specificity, are inserted manually by skilled technicians. Wave soldering under nitrogen atmosphere. This process ensures a robust connection of the components. The use of a nitrogen atmosphere minimizes oxidation during soldering, ensuring a clean and strong bond. Quality assurance and testing. Once the mainboards are assembled, they undergo rigorous testing. Visual inspection. An automated optical inspection is conducted on 100% of the units. This ensures that there are no visible defects or issues with the mainboards. Electrical test. Every mainboard undergoes a 100% in-circuit test, ICT. This ensures that the board functions electrically as intended. Final function test. Before leaving the factory, Each mainboard is subjected to a 100% functional test, ensuring that it meets the high standards set by Fujitsu. China's dominance in the tablet manufacturing and assembly industry is indisputable, with its Android tablet factories serving as prime examples of efficiency and scale. In this part, we will delve into the specifics of this thriving industry, focusing on a typical Android tablet factory in China, and emphasize the key statistics and numbers that define and drive this sector. China's leading position in the tablet manufacturing and assembly industry is substantiated by robust numerical data. Chinese manufacturers consistently command over 40% of the global tablet market share. In the year 2020 alone, Chinese tablet manufacturers collectively produced an impressive total of approximately 152 million tablets, as reported by the International Data Corporation, IDC. This monumental production output underscores China's significance in the global tablet industry. Now, let's delve deeper into the specific numerical aspects that shape the operations within a typical Android tablet factory in China. A typical Android tablet factory in China boasts an extensive workforce, often consisting of thousands of highly skilled and dedicated employees. For instance, Foxconn, one of the world's largest electronics manufacturers with numerous tablet production facilities in China, employed a staggering workforce of approximately 1.3 million employees in 2020. These skilled workers play a pivotal role in the efficient production of Android tablets. The hallmark of a typical Android tablet factory in China is its remarkable daily production capacity. These factories can produce an impressive range of tablets daily, with output rates ranging from 20,000 to 100,000 tablets per day. The actual capacity depends on factors such as the size of the facility and its production capabilities. Component sourcing. Android tablet factories in China maintain a robust network of component suppliers to meet their production needs. The electronics component market in China is vast and diverse, with over 2,000 electronic component manufacturers as of 2021. This extensive network ensures a steady supply of essential components required for tablet assembly. A typical Android tablet factory in China operates multiple production lines dedicated to printed circuit board (PCB) assembly. These production lines can efficiently assemble hundreds of PCBs per hour, showcasing the precision and scale of tablet manufacturing operations. Quality control is a paramount aspect of tablet manufacturing in China. These factories adhere to stringent quality control standards, with a focus on achieving very low defect rates. The industry norm often demands defect rates of less than 0.5%, ensuring a consistently high level of product quality. China's Android tablet factories are responsible for the exportation of millions of tablets to international markets annually. As of 2020, China's tablet exports surpassed the 100 million mark, as reported by the General Administration of Customs of the People's Republic of China. This extensive export volume highlights the global reach and influence of Chinese tablet manufacturers. Key factors driving China's success in tablet manufacturing. China's success in tablet manufacturing is driven by several pivotal factors, each supported by noteworthy figures. Cost-effective labor. China's competitive edge is significantly bolstered by its relatively low labor costs. In 2020, the average monthly factory wage for manufacturing workers in China averaged around $650. This figure is notably lower than wage levels in many other countries, enhancing China's attractiveness as a manufacturing hub. Infrastructure. China's extensive network of ports and shipping routes plays a crucial role in facilitating the importation of raw materials and the exportation of finished tablets. With 34 coastal and inland ports, China efficiently handles vast amounts of cargo annually, supporting its manufacturing industry. China boasts a well-developed transportation infrastructure, featuring over 160,000 kilometers of railways and an extensive highway network. This infrastructure enables the seamless movement of goods within the country, further enhancing manufacturing efficiency. Skilled workforce. China consistently produces a substantial number of engineering and technical graduates each year, with an estimated figure of over 4.7 million science and engineering graduates in 2020. This pool of skilled talent reinforces the technical expertise required for electronics manufacturing. Supply chain efficiency. China's vast ecosystem of component suppliers ensures a stable and efficient supply chain. For example, the presence of over 200 silicon wafer fabs in China caters to the semiconductor needs of various industries, including tablet manufacturing. Technological advancements. China's commitment to automation is evident in its deployment of industrial robots. In 2020, China boasted an astounding number of over 1.4 million industrial robots in operation, claiming the highest count globally. This automation fosters efficiency and precision in manufacturing processes. The fabrication of stainless steel pots involves various processes, one of which is forming the shape of the pot itself. One common method used in manufacturing industries is the hydraulic press forming process. Hydraulic press forming utilizes the principle of fluid pressure to shape materials. In the case of stainless steel pot fabrication, the process typically begins with a sheet or blank of stainless steel. This sheet is placed onto a die within the hydraulic press. The die is shaped in the negative of the desired pot form, allowing the stainless steel to take on the desired shape. The hydraulic press consists of two main components, the hydraulic system and the pressing mechanism. The hydraulic system includes a pump, hydraulic fluid, valves, and cylinders. When the press is activated, hydraulic fluid is pumped into the cylinders, exerting pressure on the piston within. This pressure is then transferred to the pressing mechanism. As the hydraulic press applies pressure, the stainless steel sheet is forced into the die cavity. The pressure exerted by the hydraulic system is carefully controlled to ensure that the stainless steel is formed without defects such as wrinkling or tearing. The rate at which the pressure is applied can also affect the final quality of the formed pot. The forming process may involve multiple stages, with the stainless steel sheet undergoing several cycles of pressing to achieve the desired shape and thickness. In some cases, additional operations such as trimming or piercing may be performed during or after the forming process to refine the shape of the pot and add features such as handles or spouts. Hydraulic press forming offers several advantages for stainless steel pot fabrication. It allows for precise control over the forming process, resulting in consistent and high-quality products. Additionally, the hydraulic press can accommodate a wide range of pot sizes and shapes, making it suitable for mass production. When performing metal spinning manually, meticulous attention to detail is crucial to achieve precise results. Here are some essential notes to consider when engaging in manual metal spinning. Material selection. Begin by selecting the appropriate metal for the desired application. Common materials include aluminum, stainless steel, copper, and brass. The chosen metal should possess the required properties such as malleability and ductility to undergo the spinning process without cracking or deformation. Preparation of tools and equipment. Ensure that the spinning lathe and associated tools are properly calibrated and in good working condition. The lathe should be securely anchored to prevent movement during spinning, and the spinning tools should be sharpened and polished for optimal performance. Blank preparation. Start with a flat circular blank of the chosen metal. The diameter and thickness of the blank should correspond to the dimensions of the desired finished component. The blank is typically secured to the lathe spindle using a chuck or faceplate. Setup and alignment. Proper setup and alignment of the spinning tools are critical for achieving uniformity and precision in the spun part. Carefully adjust the position of the spinning tool rest and tailstock to ensure concentricity with the rotating blank. Technique and control. Execute the spinning process with controlled movements and consistent pressure. Begin by gently pressing the spinning tool against the rotating blank while gradually increasing pressure to gradually form the desired shape. Maintain a steady speed and feed rate throughout the spinning operation to avoid irregularities or defects in the final product. Monitoring and adjustments. Continuously monitor the metal's deformation and adjust the spinning tool's position and pressure as needed to achieve the desired shape and dimensions. Pay close attention to any signs of wrinkling, thinning, or stretching, and make timely adjustments to prevent defects. Finishing touches. Once the desired shape is attained, carefully remove the spun component from the lathe and inspect it for any imperfections. Use appropriate finishing techniques such as sanding, polishing, or buffing to achieve the desired surface finish and appearance. Safety precautions. Always observe safety precautions when working with spinning lathes and metal spinning tools. Wear appropriate personal protective equipment, such as safety glasses and gloves, and be mindful of potential hazards such as sharp edges. Facility of Global Electronic Services, USA. The company's expert is repairing an electric motor. After disassembled, the stator is cutted by a special coil cutoff saw. This helped to remove one end of the stator windings so that after burn-off the winding can be easily removed from the coils. Then it is burned on the burn-off oven at high temperature. Varnish and insulation are burned off and easier to remove the old windings without damaging the lamination slots. The winding technician records data including number of slots, how many coil turns, pitch and size of the wire needed to make coils, and rewind the motor. The media blaster is used to remove the leftover varnish insulation and any contaminants. It uses a soft walnut shell to prevent any damage to the laminations but still removes any debris. After that, the stator and all the pieces of the disassembled motor are brought to a specialized machine that will steam clean and wash the parts, removing any debris or other contaminants. In the next step, insulation added to the lamination slots. An insulation paint is painted inside the stator, and liner insulation is carefully measured and installed within the stator slots to keep the coils from making contact with the stator core. The winder forms coils using the data taken earlier. Technician will need 48 coils in 12 groups of 4. The coils are then added to the stator slots and grouped according to the motor's configuration. After the coils are in place, wedging is added to prevent rotor to winding contact and to further insulate. Then the winder technician adds lacing to add strength and stability to the newly formed windings. The stator is heated to 90 to 120 to remove any internal moisture and improve varnish bonding to the coils. It is then dipped in a special varnish treatment. The varnish bonds the windings together and prevents the coil movement within the stator core. Dynamic balancing. The technician will balance and calibrate the motor. In the reassembly step, the newly balanced rotor is installed first and then the bearings. Finally, the motor will undergo dynamometer testing and painting. Kingston Technology, a global leader in memory products, has set industry benchmarks with its meticulous manufacturing processes. With its headquarters in Fountain Valley, California, Kingston's commitment to quality and innovation is evident in its DRAM memory modules. Here's a deep dive into the manufacturing journey of these modules. Design and prototyping. Every Kingston Dram module starts its life in the CAD room. Here, engineers design each layer of the printed circuit board, PCB. Once the design is finalized, a prototype is created and sent to compatibility testing labs. These labs ensure that the memory modules are compatible with various motherboards and systems they're designed for. The surface mount technology, SMT, lines are the heart of Kingston's assembly process. SMT is a method where components are mounted directly onto the surface of printed circuit boards, PCBs. This contrasts with older through-hole technology where components were mounted by inserting pins into holes on the PCB. SMT allows for more compact and efficient designs, making it the preferred choice for modern electronics. Screen printing. The SMT process in Kingston's manufacturing begins with the screen printer. This machine applies solder paste onto specific areas of the PCB where components will be placed. The solder paste is crucial as it will later melt to form solid solder joints, securing the components to the board. Automated optical inspection, AOI. After the solder paste application, the PCBs undergo an automated optical inspection. This step ensures that the solder paste is correctly applied in terms of quantity, position, and integrity. Component placement. With the PCB prepared, it moves to the surface mounting machines. The first machine places passive components like resistors, capacitors, and inductors. Following this, another machine places primary components, such as the dram chips. These machines are incredibly precise, ensuring each component is accurately positioned. Reflow soldering. Once all components are placed, the PCBs are sent through a reflow oven. Here, they are subjected to a controlled temperature profile, peaking at around 500 degrees Fahrenheit, 260 degrees Celsius. This process causes the solder paste to melt and then solidify, forming strong solder joints between the components and the PCB. Post-reflow inspection. After exiting the reflow oven, another round of AOI ensures that all solder joints are intact and free of defects. Rigorous testing. What sets Kingston apart is its exhaustive testing process. The company has developed and patented a range of testing equipment, capable of testing hundreds to thousands of modules per hour. Additionally, server-grade memory modules undergo burn-in testing, simulating 3 months of intense server usage. This step is crucial to identify and eliminate any subpar memory cells.